Okay, so Efrat's going to set up here, but Efrat's going to present on how to do advanced reconstruction methods for dynamic MRI data, where you have multiple dimensions beyond just spatial dimensions. And take it away, Efrat.
Okay, thank you, John, for the introduction. And thank you, everybody, for joining us. Good morning or good evening, wherever you are. And today I will talk about dynamic MRI reconstruction with BART. So let's dive into that. Before I start with the more technical details, let me give you a very brief introduction into what is dynamic MRI. So in dynamic MRI, we acquire case-space data over time, again and again. And well-known examples for dynamic MRI are the DCE, dynamic contrast enhanced MRI, and cardiac MRI, also known as CINE. And over here on the right, you can see an example for a DCE scan. And this is a reconstruction from prospectively undersampled case-space data that was acquired in Stanford in a pediatric DCE scan. So the topic of this presentation and the tutorial that will follow is how we can obtain such nice reconstructions from undersampled case-space data using BART. And today I will focus on an example of 2D plus time reconstruction, which means that we reconstruct a single slice in space over time. And it is easily extendable to 3D plus time reconstructions if you have a multi-slice acquisition. And usually we have one dimension that is fully sampled, so you can do this reconstruction in a slice by slice manner. Okay, so the outline of this presentation is as follows. I will first describe the BART data format and dimensionality, and then we will have an overview of the pipeline. Then we'll go into some required pre-processing steps that mainly involve the computation of the sensitivity maps. And then we will go in depth into the issue of reconstruction of 2D plus time data using compressed sensing with BART. However, this presentation contains much more information. There are many additional slides here for you to go into if you're interested. You can find there demonstrations of reconstructions of 2D plus time data using different regularizers, such as L1 wavelet in space and total variation in time and their combination. You can also find an explanation of how to extend the pipeline to 3D plus time reconstruction and explanations about how to normalize your case-space data in order to make it work easily with BART and without needing to calibrate your lambda for every different data set. So as I said, today I will focus on these topics, and there are additional slides here for you to read. So let's go into the first one. So I know that Christian covered it, but I want to make sure that we're all familiar with the basics. So let's go again into the BART data format. So BART's data format is known as the CFL format, where CFL stands for complex float. And in this format, each data or each data file is actually contained in two files, as you can see here. The first file has a .cfl extension, and the second file has a .hdr extension, where HDR stands for the header. And so most of the data is stored in the .cfl file, while the other file, the .hdr, contains information about the data, such as the dimensionality and the ordering, and so on. So here you can see an example for two files that together consist the case-space data. And here you can see an example for two maps, two files that consist the sensitivity maps. So in BART, all of BART commands operate on these CFL files. However, when we run a command like this, we don't specify the .cfl extension or the HDR. So when we run this command or other commands, you see that I just give the file name here, and BART knows to look for these two files, for the .cfl and .hdr files, and to process them together. So this is something that is good to keep in mind. We always need to have these pairs of files, but we don't specify any extension here. Okay, so let's assume that we have acquired case-space data, or maybe somebody gave us such data. And by the way, we have data prepared for you in the tutorial, and you can download it from our Git repo. We'll see that in the second half of this hour. So someone gave us this data, and we want to explore it. Let's start with exploration of the dimensionality. We can use the command BART show-m, as you can see here. And the output of this command shows us the dimensions of our data. So you can see here the dimensions. The first three dimensions are the three spatial dimensions, X, Y, and Z. In this data set, we have a single slice along the X dimension. We have a 68 by 180 pixels matrix in the Y and Z dimensions. We also see that there are 20 coils and 18 time frames. Now, the BART dimensionality convention is as follows. The BART assumes that the first 3 dimensions are always the spatial dimensions. The 4th dimension is the coils dimension, and the 5th dimension is the sensitivity maps dimension. You can use multiple sets of sensitivity maps. We will see that in the tutorial. So the first 5 dimensions are reserved, and it is highly recommended to arrange your data following this convention. However, there is some flexibility in all the other dimensions. So here, for example, we put the time frames in the 10th dimension. And when I say 10th, I mean 10 with 0 indexing. So this is the 0 dimension, and this is the 1st dimension, and so on. And this is the 10th dimension. However, you can move your temporal data to another dimension. Here you see that there are several empty dimensions. And when we will run the BART commands, we will see that in each command, we need to specify the dimensions on which BART is working. So to summarize, these dimensions are reserved. We have the 3 spatial dimensions, the coil dimension, and the sensitivity maps dimension. But here there's more flexibility, and usually we store the temporal dimension in the 10th dimension, but you can play with that. Okay. Now, let's have an overview of the reconstruction pipeline. So we have 2D plus time case space data from a multi-coil acquisition, where multi-coil refers to parallel imaging. And by the way, this can also be single coil, of course. You don't have to have multi-coils. And so we wish to reconstruct a series of images from this case space data. The main tool for doing that with BART is the BART-Pix command that we will go into in this presentation and later in the tutorial. But before we can use BART-Pix, we need to do some pre-processing because BART-Pix requires these inputs. First, it requires the case space data, of course, but it also requires the sensitivity maps. In order to compute the sensitivity maps from the data, there is a very practical and simple method. First, we will compute the average of case space data along the temporal domain. And then from this time average case space data, we will compute the e-spirit sensitivity maps. Of course, you don't have to do it like that. There are some MRI scans in which the sensitivity maps are estimated from a preliminary scan, a low resolution scan. Of course, it is also fine to use those sensitivity maps or to estimate them in a different way. But we recommend this method. It is a very practical and useful method. There are also some other optional inputs. I will refer to that later. So let's go into the first step, which is the pre-processing step. Okay, so as I said, we compute the sensitivity maps in a simple 2-step process, where the first step is to compute the time average of case space data along the temporal domain. We do that using the BART-AVG command, BART average. You see here the format of this command, and it follows the format of all of BART's commands. First, we have the name BART, then we have the command name, then we have flags and input parameters that tell BART what exactly we want it to do. Then we have the input file name, which is the case space data in this case, and in the end, we have the desired output file name. So this file name should already be in your folder, which is the data folder in this case, and this file will be created. So remember that when I say this file, BART will actually create 2 files, ksp.tfvg.cfl and a similar file .hdr. And again, we need 2 files of the ksp.cfl and .hdr. Okay, so now let's go into these parameters. What are we doing here? So first, we use the -w flag in order to tell BART not to include the 0 pixels in the average. That is because the data here is prospectively undersampled. You can see that there are many 0 pixels here. We don't want to include these zeros in the average because we don't want to shift the average towards 0. So we can tell BART to ignore them by using the -w flag. Here we tell BART which dimension it needs to perform the average on. And in this case, since we store the data in the temporal dimension, we tell it to look at this dimension by specifying this BART bitmask 10. Now, this is a different BART command, which tells BART to compute some number, the bitmask number, that tells it exactly which dimension to use. We can use multiple dimensions here. I will show this in a later command, but for BART average, we need just 1 dimension, which is the 10th dimension in this case. Okay, so once we obtained the time average case space data, which is this data here, we can compute the sensitivity maps using eSpirit. eSpirit is a well-established and a highly useful technique for computation of sensitivity maps. You can find information in these papers here. However, we don't have time to go into that today. That could be the topic of a different webinar. So I will just mention that eSpirit is implemented in BART, and you can utilize it by running the BART-Ecalib command. You can find a lot of information and help about this by running the command BART-Ecalib-H. H stands for help. And here in this case, I just want to mention that we use the -A flag in order to make BART compute the thresholds for eSpirit automatically. You can also use a manual method and calibrate the thresholds for your data by yourself. We will see that in the tutorial. So BART-Ecalib enables us to compute the sensitivity maps from this time average case-space data. So to summarize, we did two things. We computed the average of case-space data along the time domain, and then we computed the eSpirit sensitivity maps from that data. Okay, and now that we have completed these pre-processing steps, we have the required inputs, which are the case-space data and the sensitivity maps data. And in this case, we will also use respiratory soft gating weights. Now, this is an optional input. You can use that if you have accessibility to gating signals or soft gating weights. I will explain that shortly later. But if you don't have such an input and you still have dynamic MRI data and you want to do your reconstruction for it, then no worries. You can definitely run BART-Pix without this. This is completely optional. All right, so now let's dive into the reconstruction with BART-Pix. So in order to reconstruct the data from the time the temporal acquisition of the case-space data, of case-space, we will leverage the well-established compressed sensing framework. Well, this is the general formulation of the compressed sensing optimization problem, where we want to minimize an objective function that includes two main terms, the data consistency term, as you can see here, and a regularization term, which can be a single term or the summation of multiple terms. And now let's go into all of this. So in compressed sensing, in many papers, you will see that X is a single image. However, in our case, in dynamic MRI, it is important to keep in mind that X is not a single image. It is actually a series of images, as you can see here. So we have X as a series of images. Y are the undersampled case-based measurements or the fully sampled ones, or whatever you have. And again, Y is also a series of data sets, not a single case-based frame. So we have X and Y, and the A is the forward model of our imaging system. It usually includes the sensitivity maps of the coils and the forward Fourier transform operator. So we want to minimize an objective function that consists of these two terms, where the data consistency maintains the fidelity of the data to the measurements, and the regularization term enables us to use some a priori knowledge about our data.
Efrat, a quick question on the last slide. So normally when we see the compressed sensing problem written out, there's only one regularization term here. So can you just talk about a little bit about what you're saying here with this sum over multiple regularizers?
Yes. So we can use several regularizers if we know, for example, that our data exhibits sparsity in the wavelet domain, and it also has smoothness along the temporal domain. Then we can use a regularizer for sparsity in the wavelet domain and add to it a regularizer for the temporal domain. This example, which I just described, appears in these slides in the additional part, and it also appears in an additional Jupyter notebook. You can have a look at it. But indeed, usually we have just a single regularization term, and we will see that in a minute. Okay, so the more you know about your data, the more you can use for the optimization problem, of course. I think that once we'll go into an example, this will be more clear. Okay. Okay. So in BART, we solve compressed sensing problems using the BART-Pix command. And as Christian mentioned, PIX stands for parallel imaging compressed sensing. However, this command is also applicable to single coil imaging, but we use the name BART-Pix. And so BART-Pix is our hero today. This is the focus of this tutorial. If you want to get help about BART-Pix, you can run this command, BART-Pix-H. It will give you a lot of information about the different optimization problems that you can solve. This is a very powerful command. So you can do a lot of things with it. I'm not going to go into all of this. You can have a look at the help later. And today we will focus on a single implementation, which is the compressed sensing with locally low rank regularization. Before we go into that, let's see the general structure of the BART-Pix command. I know that Christian showed this, but I want to go over it again so that it will be clear for everybody. So as in all of BART commands, we have the name BART in the beginning, the command name, which is Pix. Next, we have a series of flags and arguments that specify what we want to do exactly. And here in the end, we have two input file names that are necessary. First is the case-based input file name, and second is the file name of the sensitivity maps. And in the end, we have the output file name. Now, again, I want to mention that all of these are CFL files, but we don't mention the CFL extension. We just give the general file name. And now that you are familiar with this structure, let's go into the flags and let's see how we can solve our dynamic MRI reconstruction problem. So today we will focus on the -R flag, where R stands for regularization, the objective function. And we will solve this general optimization, but we will solve it with a single regularizer of a locally low rank. We will see that a bit later. I just want to mention that if you want to get help and if you want to see which kind of regularizers you can use here with BART-Pix, then you should run this command, BART-Pix-RH. And let's quickly go over the output of this help, not over everything, but some of it. So this is the general structure of the regularization flag in terms. So R stands for regularization. T, the first argument, stands for transform. And you see here that you can use multiple or different transforms, such as the wavelet transform or the total variation transform. A, the first argument, and B, the second argument, specify parameters that are related to the transform that you chose. And C is usually the regularization parameter lambda that you see here. For those who are interested and want to work with L1 wavelet and total variation, which are two very useful examples or transforms, we have examples for you in the additional slides and also in an additional Jupyter notebook. You're more than welcome to go into them later. By the way, all the slides are self-explanatory. You can read them and hopefully learn from them. And today, as I said, we will focus on this example of the locally low rank regularization. So we have L for locally low rank. We have several parameters that I will explain, and we have here an example for lambda, the regularization parameter. So to summarize, this is BART-Pix, the command. This is the general structure. The -R flag enables us to specify which regularizer we want to use, and by that we specify the compressed sensing problem that we're going to solve. One thing that you need to know is that since the data consistency term, this term, appears in all the compressed sensing optimization problems, then you don't need to specify it. BART-Pix knows that it is there and it will solve it. It will include it in the optimization problem. You don't need to do anything about that. It's always there. So BART-Pix, and you can use BART-Pix-RH in order to get this help and learn about these transforms. All right, so now we're going to go into dynamic MRI reconstruction and see how we can solve our specific problem of 2D plus time data reconstruction. So in dynamic MRI, I want to explain first what is a low rank, and then I'll show you how we can solve the compressed sensing problem with the low rank regularizer. So in dynamic MRI, we can reshape our data and build the so-called Casarati matrix, which is a spatio-temporal matrix. We can take each frame of our data and simply reshape it into a column, where R is the reshaping operator. So we just take this data and present it differently. And of course, we can do that for every time frame in our data set. And by putting these columns all together, we obtain the Casarati matrix. This matrix, which is nothing but a spatio-temporal matrix that describes the same data in a different way. I'm sure that this is simple for everybody. And by doing that, we can notice that there's a lot of similarity between the rows of the Casarati matrix. And this tells us that the matrix has low rank. There's a lot of dependency here. And it turns out that many MRI datasets and dynamic MRI datasets in general exhibit this low rank property. And it also turns out that low rankness of the data is very useful for reconstructing the data from undersampled case-based data. That's because if you have a priori knowledge about your data, you can use this knowledge during the reconstruction in order to improve the reconstruction and seek a solution that will be consistent with this a priori knowledge. So in this case, we will seek a solution that will give us a Casorati matrix that has this form. It has a lot of redundancy and dependency between the rows, and which means that it has a low rank. So if we're going to work with the general matrix, the Casorati matrix that is formed from the full time frames, we will say that we seek a solution with a global low rank. The word global refers to the fact that we took each of the time frames, we reshaped them into the matrix, and we got a single matrix that describes our data set completely, the full data set. However, we can also do this reshaping operation for patches, of course. So in this case, we can take a small patch, and we'll take a series of patches in the same location across the time domain. We will reshape them where Ri is now the operator for reshaping patches, and I stands for the patch location. And then we will obtain this small Casorati matrix. And now, since the global data, the general timeframes exhibit low rank, we know that also the small Casorati matrix will also exhibit the low rank property. And of course, we can do this operation for multiple sets of patches and obtain multiple small matrices, Casorati matrices. And it happens so that all of these matrices will exhibit the low rank property. And this is again very useful for reconstruction. In fact, there are papers showing that the locally low rank feature of the data is stronger than the global low rank feature of the data. That's because the patches tend to behave in a similar way along the time dimension. Yes, okay. So now let's see how we can use this information for solving our optimization problem. So we can work and we can solve either one of these two compressed sensing optimization problems.
Fred, there's a quick question, whether the reshaping also flattens the coil dimension.
That's a good question. So we don't do that on the multi-coil data. We do that on a single image that is obtained from the data using the adjoint operator. So let me go back to the compressed sensing slide here. So X is, you can see here that X refers to a single image, not the multi-coil image, because the forward operator already includes the coil combination. We don't do that for specific coil-specific images. We do that for the single image that is reconstructed from the multi-coil data.
So in other words, the regularization is applied to the image, not to the coil data.
Yes, thank you. And are there any other questions?
We just got a couple. Okay. How do you reformat the spatial temporal matrix into the Casorati matrix? Is this something that you have to do yourself? And if it's implemented already, just could you explain how that's actually what's actually happening here?
Yes, so you don't need to do that for yourself. You just need to give BART the k-space data, and BART will do this for you. It's not something that we do actively. We just give BART not even this data, not the image domain data. We give it the k-space data and the sensitivity maps, and this is something that happens automatically during the iterations once we solve a compressed sensing problem with a low rank regularizer. Okay, so I was just showing this in order to explain the concept of low rank. It's not something that you need to do. You do not need to reshape your data. You give BART the k-space data, the time frames in the k-space domain without reshaping them.
And another question I think can be quickly answered. Question was, if you're using single channel image, why do you run eSpirit? But I think you're actually using multi-coil data, and that's why you're running eSpirit.
Yes, that's true. So in this example, or in the example that we'll see in the tutorial, we will focus on multi-coil data. Yes, if you have a single channel image, then you don't need to run eSpirit.
And another question is about non-Cartesian data, how this spatial temporal matrix could be calculated. Maybe I could quickly answer that. So again, even though the data itself is non-Cartesian, we're still reconstructing an image on a grid, and the regularization is always being applied in the image domain to our final image result. So the spatial temporal matrix is still created in the same way, whether we're using non-Cartesian case-based data or Cartesian case-based data.
Yes, thank you, John, for explaining that. And if I can add, what's happening during the iterations is that we use the non-uniform Fourier transform in order to interpolate our data and reshape it into a grid, into a Cartesian grid. And so, as John said, this is always happening in a Cartesian grid. Okay, so I hope that this is more clear now. Are there any other questions, or should we move on?
I think you can continue.
Okay, thank you, John. Okay, so we talked about the fact that we can reshape patches, and now let's have a look at the compressed sensing problems. So if we work with a global low rank regularizer, then we solve this compressed sensing problem, and I will show you in the next slides how we can tell BART which problem we want to solve. But first, let's just talk about the compressed sensing problems. So if we want to implement a global low rank regularizer, it is this regularizer. Well, our regularizer, you see, it consists of the nuclear norm. This star here stands for the nuclear norm, which is the sum of singular matrix values of the matrix. And the Rx is simply the Casorati matrix, this matrix, because R is the reshaping operator for the full time frames. So if we want if we know or if we assume that our data exhibits the global low rank feature, then we can use this regularizer. And then we will seek a solution that has this property, a global low rank. However, if we also assume that our data has the locally low rank feature and we want to solve for that one, then we solve this compressed sensing problem, where Ri stands for now extracting patches. This is the operator that extracts patches along time and forms the small series of Casorati matrices. And by using this regularizer, we will find a solution that has a locally low rank feature. So, if we want to work with low rank, to summarize, we can solve either one of these compressed sensing problems. And if you would like to learn more about this topic, there are very good papers for that. I encourage you to go into and read them. And now let's see how we can solve these problems using BART. Okay, so this is our compressed sensing problem. I formulated it here for the locally low rank feature. And we solved that by using the BART-Pix command with the -r flag that we've seen before. And now, in a minute, I'll go into more details. Are there any questions now, John? I see that there are a couple of...
No, go ahead.
Okay. So we have -r. We have L, which stands for local low rank or just low rank, because we can also implement the global low rank here. And we have these two arguments that I will go into in the next slide. And in the end, we have lambda. You see, lambda is the parameter here. This is a parameter that controls the trade-off between the data consistency term and the regularization term. So once we give BART these details, the -r and the low rank flag, BART already knows that we are going to solve this compressed sensing problem. And now the question is, are we going to use a global low rank or a locally low rank regularizer? And let's see that in the next slide. So I'm going to show you a few examples of how of the parameters that we give BART and how BART interprets these parameters and what is actually happening. So let's focus first on the first bit mask, the first argument. This bit mask tells BART how to form the Casorati matrix. It actually tells it which dimensions we want along the matrix, along the first dimension of the Casorati matrix. So here you can see that we have dimensions 0, 1, and 2, which stand for X, Y, and Z. And this tells BART to put these dimensions along the rows dimension. All other dimensions, the ones that we didn't specify, will become the second dimension. Since in our case we have only the T dimension, this will become the second dimension of the Casorati matrix, and BART will build this matrix for us. We don't need to do it. We just need to tell BART which dimensions we want along this column here. And now what about the second flag? The second flag actually enables us to determine whether this will be a global low rank or a locally low rank regularizer. If we put 0 here, then 0 tells BART to not split the data into patches, and this will implement a global low rank regularizer. So 0 means global low rank. But let's go into the next example, which is almost the same example. The only thing that was changed is this, the second argument. So here, if instead of 0, we give BART dimensions here, This tells BART which dimensions we want to split into patches. And since we gave BART here the same dimensions, the 0, 1, and 2, BART will create patches. BART knows where it puts these dimensions in the casualty matrix. We don't need to do anything, not to build it and not to split it. We just need to tell BART what exactly we want to happen. What do we want from it, basically? So if we have these dimensions here and these dimensions again here, the second argument tells BART to split the data into patches. And so now we actually create a series of small casualty matrices. And now this means that we're going to solve the locally low rank compressed sensing problem. So to summarize, we can tell BART if we want a locally low rank or a global low rank regularizer by specifying the second argument. We need to have all of this information for BART. We need to have the -R flag. We need to have L for low rank. We need to have the first dimensions here to specify how we want to build the casualty matrix. And again, the dimensions that we specify here will become the column dimension, and the other dimensions will become the second dimension. And we need to tell BART here whether we want a global low rank or a local low rank argument, not argument, but regularizer. And now let's see a slightly different example. We can also do it in a very different way. There's a lot of flexibility here, and let me show you this. We can also tell BART that we want to put actually the time domain along the first dimension. Now remember that I told you that all the dimensions that we didn't specify here will become the second dimension. So when BART sees this, it builds the casualty matrix like that. The time dimension is now here, and all other dimensions are here. And here we also told BART to split the data into patches along these dimensions, X, Y, and Z. And BART knows where it put these dimensions. And by the way, it's very important to understand that this relates to the original dimensions of the data, not to the X dimension here of the casualty matrix, to the original dimensions. So once we give BART this information, it will split the data into patches along these dimensions because it knows where they are. And it happens so that again, we implemented the locally low rank regularizer with these input arguments here. So by formulating our problem like this, we actually solve an identical problem to the previous one where we formulated it like that, because this matrix is the same as this matrix, or actually the series of matrices is the same as this series of matrices, and we will get an identical solution because it's basically the same problem. So to summarize, we have seen several options, but I just want to mention one last thing. By default, all of BART's blocks are of size 8 by 8. That's the default, but you can also specify the patch size or the block size by using the -B flag. Well, here we specify the number 20. This means that we will have 20 by 20 blocks. So the casualty matrices will be a little bigger. We will still create a series of them because we specified this information here. So to summarize this part, we have seen the reconstruction pipeline. We have seen that we can compute the e-spirit sensitivity maps from the time average case-space data, and we have seen how we can reconstruct the data using BART peaks. I just want to go very briefly over the issue of soft gating weights because we will see this in the Handson tutorial. So let me just take a minute or two to describe this, and then we will move on to the Handson tutorial. If you want to get your Jupyter notebook ready for that, then you're welcome to open it in your machine. And let's go for a moment into this. So the soft gating weights are ways that enable us to weigh case-space data according to a gating signal. We can use, for example, a hard gating method where all the weights, both for soft gating and for hard gating, are implemented into the compressed sensing problem using this W matrix here. So W is a matrix that multiplies the data consistency term. And we have the weights. It is a diagonal matrix, and all the weights are positioned along the main diagonal of the matrix. So if you have a gating signal and you know that some of the data is corrupted, you can use zeros and ones here on the diagonal to include or not include some of the case-space data according to your signal. Here we're going to use in the tutorial soft gating weights. Soft means that the weights have zeros between 0 and 1, and this means that we can weigh down case-space data that we know from respiratory data which is corrupted. So in order to mitigate motion artifacts, we will use the weights to weigh down some of the case-space data. You can see here, for example, how this affects the reconstruction. So this is the conventional reconstruction. We have case-based data, and we obtain this reconstruction from it. And by weighing case-based data, you see the weighing here, you see that some of the data is less strong now. And by doing that, we mitigate motion artifacts, and you see that the reconstruction becomes sharper. But as I said in the beginning, this is completely optional. If you don't have such a signal, you can still, don't worry about that. You can still run BART-Pix and get your dynamic MRI reconstruction. So to summarize this presentation, the take-home message that we would like you to remember is that BART-Pix is a very powerful command. You can use it for solving many compressed sensing problems, and specifically for the aim of solving the 2D plus time reconstruction problem. You can specifically, even more with a locally low rank or a global low rank, you can run either one of these commands to obtain the regularization and obtain your solution. Just don't forget to specify which flag exactly you want here, because this determines which problem exactly you're solving, the global low rank one or the local low rank one. And as I said in the beginning, there are many more slides here. Let me just show you again the outline. You can learn how we can solve compressed sensing problems with L1 wavelet, with total variation, and even with two regularizers together. And you can also learn about 3D plus time and case-based normalization. So if you have the time and you're interested, then you're welcome to download the presentation. It is in our Git repo, and go over these slides. Okay, are there any questions, John?
No more questions. I think it'd probably be good to move to the exercise.
Yes. Mm-hmm.
And if there's questions in the meantime,
We'll
feel
take them
free to ask.
Okay, so I'm going to share the Jupyter notebook.
So again, if you're running this in the binder, it'll probably be slower than running it locally, especially now that we're dealing with multidimensional data, whereas the previous example was a single image. Now we're reconstructing a time series. But you could still run this through the binder if you don't have it set up yet.
Okay, so I hope that everybody is ready. You're more than welcome to follow it here in the Zoom and view my screen, or in binder online, or in your own Jupyter notebook, however you find more convenient for you. Okay, so welcome to the second part of this tutorial. And here we will show you how you can actually reconstruct data from subsampled multi-color case-based data, which is 2D plus time data. We have the installation instructions here for you. Please notice that this new Jupyter notebook, unlike the previous one, is running with a Python kernel. So what you need to do is, in order to run it, is first to add BART to the toolbox path. You can do that, and second, you need to add the Python path, which is the same path as BART, but with a /Python. So in order to do that, the recommended way is to edit your bash.c file. You need to open that in your Linux terminal and to edit it. You need to add these 3 lines. And then after you do that, don't forget to resource your bash.c file, or just to start a new Linux session. However, if you don't want to add your bash.c file, you can also add these commands to this specific Linux session or Jupyter notebook session. You can import sys and OS, and you can run these commands here. Of course, you will need to change that from my path to your path. Just keep in mind that this will affect only this session. Once you close it, it will not be effective anymore, and it will, of course, not be effective for other Jupyter notebooks. So it is more recommended to follow these instructions. This only takes a minute, and to install BART permanently. Okay, so let's assume that we all installed BART, and we can import some general packages. We also need to import BART and the CFL package, which enables us to read CFL files. And as an option, you can also install SigPy. SigPy is a very useful package for processing of signals and images in Python. Here in this tutorial, we only use SigPy for displaying the reconstructions, so this is optional. Excuse me. However, if you're interested, then you can, of course, install SigPy and run it. So here we will show different examples for loading your data and displaying it, both using Matplotlib and SigPy. Okay, let's see that it's all working. We run this command. And for those of you who are less familiar with Jupyter Notebook, I want to say that while we are running this Jupyter Notebook with a Python kernel, we can also run Linux bash commands using this exclamation mark. So whenever you see an exclamation mark in the beginning of a line, this means that we are now running a bash command. But if we don't have that, then we are running a Python command. This is very useful because now we can interact with BART both using the bash interface, the command line interface, and the Python interface. Okay, so we have prepared some data for you for this tutorial. The data is located in the data folder. We can have a look at it. And here you will see many files because I already ran this reconstruction. When you run it in your Jupyter notebook, you will see in the beginning just the case-based files and the maps files. And as we said before, we have this pair of files, the .tfl and the .htr files. We also talked about BART's dimension convention. I think that this is clear now, so I hope. So let me move on and show you the data dimensions. So again, here we're going to use this interface, and we will run the bash command, the Linux command bar show-m in order to see the dimensions of our data. And by running it, you see that we can see the same dimensions as we saw in the presentation. We have a single slice in the X dimension. We have 68 by 180 pixels in the YZ plane. We have 20 coils, and we have 18 time frames. And of course, the data is arranged according to the BART data format. You can also do that. You can also, look at the weights. I'm not going to do that now. It has almost similar dimensions. The only difference is that there's no coil dimension for the weights because we use the same weights for all the coils. So if you want, you can run this command and have a look. This one. Okay. Another option for looking at our data is by importing it. And by importing, I mean that we're going to import it into a NumPy array because this is a Python Jupyter notebook. So let's do that. And once we have this case-based array, which is a NumPy array, we can use all of NumPy's features such as .shape, and this gives us the dimensions again. Okay, so now we have this data and we want to explore it a little bit. Let's say that we want to visualize the sampling mask. We can do that easily. We can leverage a useful tool named BART pattern. This command will examine the undersampled case-based data and will produce this sampling pattern from it. So this is the input to the command, and this is the output that we're creating. And let's run this. This is very quick. And after that, we can look at the data that was created the by running BART show-m data path. And you see that we created a data file that contains the case-based sampling masks for all the time frames. You see the temporal dimension here. And of course, we don't have the coils dimension again because we have the same masks for all the coils. So now let's visualize this data. We're going to import this data into a NumPy array. And once it is in a NumPy array, we can plot it using matplotlib. So this is basic code for plotting. I won't go over it, and I hope that you can all that you're all familiar with it. And here, for example, I plotted 3 different time frames, and you see that the sampling pattern changes a little bit. That's the acquisition that was in this specific data set. And of course, you can do that for all of your time frames and see the sampling pattern. Okay, we can also view our data with SIGPy. I will just show this once. You need to transpose the data because SIGPy assumes that the temporal dimension is the first dimension. So you have some code for that here. And we can run this. And here, SIGPy has a very nice and useful feature. You can page through the data. So since we generated all the maps, we can move between them. And by moving, I mean that I'm doing that with the up and down arrows. So you can use the arrows on your keyboard and you can move. Just make sure that the inner brackets are appear along the temporal dimension because SIGPy pages through the dimension that you tell it to page through by these brackets. So by using your up and down arrows on your keyboard, you can move between the sampling masks of the different time frames. And of course, once you obtain reconstructions, you can also display them like that and move between your reconstructed time frames. Now let's move on to the sensitivity maps estimation. So as I said in the presentation, we can first compute the case-based average over time, and then run the Spirit tool for computing the sensitivity maps. So that's exactly what we do here. You see that we computed the case-based average and we showed its dimensions. And now we can also run BART eCalib in order to compute the maps. You see this is also quite quick. Here we didn't use -a, we used specific thresholds that I calibrated before. You can calibrate the thresholds for your own data or use -a in order to have BART compute them for you. Here it is important to notice that I use the -m with the number 2. This means that we create 2 sets of sensitivity maps. This is a feature of eSpirit that eSpirit enables us to have multiple sets of sensitivity maps. This is highly useful for reconstruction of dynamic MRI data. I'm not going to go into that now. You can find the details in the eSpirit paper and in the BART-Equalib help. So if you want to get more help about that, you should run BART-Equalib-H. And let's have a look at the size of the sensitivity maps. You see that we have the same dimensions in the X, Y, and Z space, and we have the coils dimension here. And there's no time dimension here because we use the sensitivity maps for all the time frames. We have computed them from the time average k-space data, so we already collapsed the time dimension. Next, let's load and display the sensitivity maps. So as before, we read them using the CFL package into a NumPy array, and we can display them using matplotlib. And here we can see the first 12 sensitivity maps. You see that they're very nice and of course very useful. As an alternative, you can also do that and all of the other things that we're doing here using BART's Python binding. The general structure of BART commands in Python with the Python binding is as follows. We have the output file name on the left. We have BART here, and in brackets, we need to specify all the arguments, the number of arguments, the command that we want to run, and the input arguments. And as an example, I prepared the code for the commands that you ran above. I prepared it here for you in Python. You can run this later offline. You see these are the same commands. Of course, they will produce the same output. They're just formulated differently. You can use the BART interface like that. And here BART creates not a CFL file, but a NumPy array. And you use this NumPy array for the following commands, or you can store it as a CFL file like that. Okay, so now let's move on to the reconstruction, which is the main part of this tutorial. So as Christian said, you can run BARTPix-H and run BARTPix-RH to get help about these two features of BARTPix. And now let's get to the main part, which is the local low rank compressed sensing problem that we want to solve. So in order to solve that, let's see how we do that. We have the k-space data ready in the data folder, and the sensitivity maps that we have estimated are also saved in the data folder. You can see that here. And you can run BARTPix. Here we have sorry, excuse me, it's my computer not handling Zoom very well. So let me just say that we give after the number D, after the -D, we give the number that specifies the debug level or the output level. You can have 0 or 1 here if you want to get less output, but it's almost always useful to have a lot of outputs to see what's going on. You can specify the number of required iterations. You don't have to. There's also a default for that, but you can if you want. Here we use the -P flag in order to include the weights in the reconstruction. These are the optional soft gating weights that I showed you. And here we have the most important part, which is the regularization flag and all the parameters. So you see that we have R for regularization, L for low rank. We have these first 3 dimensions, which are the X, Y, and Z dimensions. This tells BART how to form the Casarati matrix. And we have also specified these dimensions here again, which means that we are going to solve the local low rank problem. This is the lambda. And again, this is the k-space input, sensitivity maps input, and this is the output file name. So by running this, I'm not going to run it now because it takes a few seconds and I want to move on, but by running this part, we'll compute, do all the iterations and we'll compute the solution for us. We can now load the solution and have a look at it. So here what I did is just use again this read CFL command for loading the data into a NumPy array. And I squeeze the data so that we can look at it, and I use some basic matplotlib code to present the data with matplotlib. And we can see the different time frames here. We can also present this with SIGPy, and as I told you before, you can page through the different time frames of the reconstruction by using the up and down arrows of your keyboard. So you see that we obtained a nice reconstruction, although our data was prospectively subsampled with a reduction factor of more than 5. Okay, one last thing that I want to talk about is how to correct the aspect ratio, because when you look at this image, it seems that the image is a bit squashed along one dimension. right? This doesn't seem so natural to us. That's because K-space data was acquired with a non-symmetric pixel size, which means that in the MRI scanner during the acquisition, the K-space pixels they had an aspect ratio that wasn't 1. They had different lengths in the Y and Z dimensions. And so if we want to fix that, what we need to do is to convert the data to transform it to the Fourier transform domain and do some zero padding in order to restore the original dimensions of the data, and then convert it back to the image domain. You can do that very easily with BART. We have the BART FFT command for the forward Fourier transform. Mickey, maybe you want to mute, perhaps. And so we can do the forward Fourier transform to obtain the data in the Fourier transform domain. And then we do resizing, we do zero padding, and then we will do the inverse Fourier transform. And I know that you're asking, how did you know how much to resize to? Where did you get this number from, right? Because that's the most important thing. How do you know the true dimensions of your data? So for that, you will need to go to the MRI scanner or to the person who gave you the data and ask them what was the field of view. And you need to compute from the field of view, you need to compute the true aspect ratio, which may be 1.5 or 1.8 according to your field of view. You need to know basically what would be the true matrix size if you had the full K-space data, and then you need to pad it to the correct size. So here I used 100 just in order to get the right image size. Now let's load the data and see the difference. So this is the data that we reconstructed before. And this is the same reconstruction, but after we fixed the aspect ratio by doing this process of a forward Fourier transform, zero padding, and then inverse Fourier transform. So I didn't change the reconstruction, I only zero padded it in the Fourier domain. And this, of course, seems like a more natural MRI image to us. MR image, sorry. Okay, so we have gone through everything, and now we have a little bit more time for a hands-on tutorial. We prepared a second data set of a DCE scan for you. You can find it in the DCE CComp folder. This is because the data was already compressed into 6 calls. You see the dimensions here. Now everything is ready for you. We have the K-space data, which is named K-space slice 80 because this was a slice that was obtained from a full 3D volume acquisition. We computed the sensitivity maps also for you. You can either follow these commands and run them yourself, or just use the data that you already computed and saved. And now it's time to do your own DCE recon. We have a few minutes. So please, everybody, go ahead and open your Jupyter notebooks and put your recon here. What you need to do or encouraged to do is to run the compressed sensing reconstruction with a local low rank or a global low rank reconstruction, and your data is here. This is the data CComp, K-space data, and in the same folder you will find the sensitivity maps. So I will give you a few minutes to do that. It's only a single command, and it's very, very similar to the command that we have seen before for the previous data set. And of course, you can find it up here. So please go ahead and do that if you're interested. And while I'm waiting, maybe we can take some questions. John, are there any questions?
Yeah, let's give a minute for people to do the exercise. There were a few questions that I answered directly in the chat. So one question was if there's a difference between the transposed low rank matrix and the non-transposed, and because we're doing singular value thresholding, they give the same result. There were a number of questions just generally how to use the compressed sensing tool when there's no coils, when it's a single channel data. And so for that, you can use the parallel imaging compressed sensing tool, but you have to pass it sensitivity maps that are all ones that match your data size. So then you can use the same PIX command with single coil data.
Exactly, yeah. Are there any other questions or issues for discussion?
Not at the moment.
Okay, so I hope that everybody's working on that. It should be just a single line here. And I recommend to use the command line interface. So your line should start with the exclamation mark, then BART-PIX, then you need to specify all the other parameters. And if you copied the command from above, then don't forget to change the data folder name and the file's name. And you can also play, of course, with the path size, with the lambda. We have some recommended values here for you. And And don't forget to run it. And oh, by the way, the output file name should be as it appears here, recon-LLR, not dash, sorry, recon_LLR, because then you can use this code to upload and present your data. If you change the output name, then please also change it here.
So Efrat, since we only have a few more minutes, do you want to show what you would do here and then kind of wrap up?
Yeah, yes. So I have the solution already down here. If you don't have that line in your notebooks, but you do have the solution in your Git repo. You just need to look for a text file, a simple text file that is called lr_solution.txt, and you will find it there. So let's run this command quickly. So as you see, it is the same, almost the same command as we had before. We added the weights. Sorry, we added the regularization term and the case-based data and the sensitivity maps data. Let's run this. It will take a few seconds. Sorry, it doesn't run because I forgot the exclamation mark. Okay, now it is running. Let's give it a few seconds. Basically, it is the same process that we have seen above. We do locally low rank, we do compressed sensing reconstruction with a locally low rank regularizer. Of course, if you put 0 here, then you will do that with a global low rank. That should also give you a good reconstruction. So we see that it took only a couple of seconds, and let's load our reconstructed image. You can see it here. You can also page through it by using the arrows. And as before, we need to correct the aspect ratio by doing 0 padding in the Fourier domain, and then we get this reconstruction. So I hope that you all got this. I hope that you all got this image or something similar to it. And that's it. So to wrap it all up, today we learned about BART-Peaks. We learned how we can use this powerful tool both for sense, as Christian showed, and for dynamic MRI reconstruction. And I encourage you to go into the help of BART-Peaks and learn more, and to go into these tutorials, and there are other tutorials available, and to learn more about the different things that you can do with BART in order to reconstruct images from your data. Yeah, thank you, John. Back to you.
Yeah, thanks very much, Efrat. That a lot of really helpful information there. And a lot of these techniques also extend to data that has multiple extra dimensions. So it could be respiratory motion and cardiac motion and contrast and relaxation. And so this interface is really helpful for processing these highly multi-dimensional data sets. So we just have a couple minutes left. I know we kind of pressed for time at the end there, but we really encourage you to go through the exercise. And if questions come up, we have a mailing list, and all of the details for those things are on our website, which is in my Zoom background. Also, for those of you who indicated that you want to be contacted again, we'll send an email about the next upcoming webinars to our mailing list, as well as to you if you want to get those emails. Any last questions before we wrap up?
Maybe just a comment. If you have any feedback for us,